and I'm very happy to start with tonight's workshop, um, Turning Japanese Handwriting into Data with Richard Harris from the Cogent Labs. And as usual, we will start from a very short intro about Wagon delivered by our CEO, Sylvain. Go ahead.
Thank you so much, Sasha. Cool. I won't share slides today. Sometimes I do, but today I thought I would make it short. So yeah, thank you very much for joining us for this talk by Richard. I actually did not have the chance to meet Richard yet, but we had a quick talk over Zoom, and he was really excited about giving a talk about what they do. I mean, some of what they do at Cogent, and so as some of you probably know, at Le Wagon, we teach programming and we also teach data science, and we like to organize events and workshops and talks like this one to kind of open up different ideas and perspectives around tech entrepreneurship, or slightly more technical talks like the one that we'll have tonight. So as I was saying, we at Le Wagon teach web development and data science. We do that through 9 weeks or 24 weeks program. And so specifically the talk of tonight is more related to what we do with data science. So we wanted to give a little bit more perspective for our data science students, and also potentially to people who would be interested as well as joining our future bootcamps. So if you are interested in discovering a little bit more about what we do at Le Wagon, I believe that Sasha is going to share a link. Thank you, Sasha. But for now, I leave the floor to Richard for his talk. Thank you so much.
Thank you. Thank you for the introduction, and thank you for the invitation to present here. I hope everyone can hear me. Can someone comment? Yeah, cool. Okay, so I am here from Cogent Labs, company in Tokyo, and I'm going to talk about sort of one of the strands of work we do, which is to do with OCR, Optical Character Recognition. But first, a brief comment about who we are, Cogent Labs. No. Here we are. Our sort of our tagline, our kind of motto, is to shape the future with artificial intelligence. We are a startup in Tokyo, primarily at the moment focusing on kind of Japanese businesses, kind of business process automation for various issues that people have in Japan. I don't know, it seems like there's people from all over the country, not over the country, all over the world. So maybe not everyone here has the best context on Japan. But there's still a lot of, I mean, as in many countries, there are lots of business processes that are still very kind of manual. And the idea being that like these are things that kind of are ripe for automation. And if you can do that, then you can free up the people to do kind of hopefully more sort of productive and kind of more sort of inspiring things. So in terms of what we do at Cogent Labs, as I said, there's sort of a few strands of kind of what we've got to do. So the one I'm going to talk about tonight, which is sort of our largest, kind of most mature project, is something called Tegaki. So if people who are not familiar with Japanese, Tegaki is actually the Japanese word for handwriting. So it's an OCR engine. That it's sort of, I mean, it can read printed characters perfectly well, but it's sort of specialized particularly for handwriting. And handwriting is a very difficult, very difficult problem, particularly for Japanese, which is one of the things I hope to convince you of in this talk. So here's a bunch of various images with sort of some nice handwriting and some kind of quite nasty handwriting, I would say. That we can still nonetheless read, so very high level of accuracy. And I think you can see some of the challenges already that like this is sort of like this kind of thing here, right? It's already been kind of quite nastily cropped. It's probably gone through some 1980s fax machine, and it's been kind of written in quite a quite a hurry, it seems. So there are lots of problems when it comes to actual kind of real handwriting, because printed is OCR is more or less a solved problem. I mean, maybe that's overstating it a little, but printed OCR is maybe not particularly challenging domain, but handwriting, particularly when people are free to write however they want on various forms, that is indeed a challenging problem. So Tegaki is the kind of the largest of the things that Cogent works on right now, but we also have another kind of, we work on many areas, but the other kind of main thing we work on is natural language processing. So here we have Kaidoku, which is our sort of general name for our various NLP offerings. We've recently launched this product called SmartFind, which is meant to be like a Google search engine for your own business. So that many businesses have all these kind of documents built up over time that they're not like properly indexed. It's very difficult to know what you want, and maybe someone knows about it somewhere, but it's very easy. It's very hard to go through all the company's data and find the thing you actually want. And so we're leveraging kind of NLP techniques, kind of specifically like kind of QA models and various things like that to make this possible. And I think these two products, Tegaki and SmartFind, the idea is that they can work quite nicely together, right? So you have all these documents, and it's not enough just to read them. You want to be able to read them and also to interpret them. And if you kind of put these together, that's quite a powerful thing. So those are, I guess, the two main strands of what we're doing with Cogent at the moment. As for Cogent ourselves, I guess this is our sort of, mission statement. So as it says here, we're trying to take the latest in research, latest kind of techniques, and apply them to sort of real world business problems, particularly in Japan, but not just in Japan. We do work more internationally as well. And it's actually quite an interesting environment here. So I don't know if you can see me. I'm in this sort of, our office, I would say it's quite nice. We're in Roppongi. There's a sort of a view of Mount Fuji on a particularly nice day. The company is, I think it's only still about 4 years old, something like that. I've been here for about 2.5 years. And it's under 100 people. I don't know the exact number, but even if it's under 100 people, but there are 19 different nationalities represented here. It's a very, very international company, very international kind of group of people I get to work with, and that's kind of I really enjoy that. It's quite that's quite cool. And we are, this is the plug. If you like what I go on to talk about today, we are indeed hiring. We're particularly looking for machine learning engineers at the moment. And maybe just to give a brief introduction to me myself. So yeah, my name is Ritaris. Actually, about 4 years ago, I did a similar kind of boot camp to the one that Wagon runs back in London. So my background is I did maths. I did a PhD in maths in the UK at Cambridge in sort of differential geometry type stuff. And then I moved into software, and I kind of found that wasn't quite right for me. And then I gradually over time moved towards sort of data science, machine learning. And now I'm at Cogent Labs. I'm head of the machine learning science team here, so the team that kind of really builds the models that power what we do. So that's me, and that's us. For what I want to talk about today, I am indeed going to talk about sort of OCR and sort of the challenges of how on earth you can read this Japanese handwriting. There's going to be basically two halves to the talk. I'm going to first talk about some kind of theory, what the state of play is. And then later on, I'm going to talk about some of the actual problems you hit when you try to do this stuff for real. Because that's indeed the challenge. There's a lot of, research out there that is still very difficult to take to production, but we are really all about building products here. Okay, so theory. I think it's probably fair to say that OCR is not the the hottest research topic in the world, but there is actually nonetheless quite a lot of interesting stuff there. I think in terms of things that have made a bit of a splash, I think this is probably a good example. So this is something called Kuzushiji. So this is old Japanese handwriting, according to a script that actually most Japanese people can't read today. It's a sort of an old variant of modern kind of hiragana. And so there are lots and lots of books and the various documents, artifacts that if you can digitize this, that's quite a lot of use. That's quite a lot of interest to historians, social scientists. So what you want to do is to go from this to this. You want to kind of be able to find and transcribe all this data. And so this has actually kind of made a little bit of a splash in the research scene. It's got quite well known. It's quite an interesting application. And so I put the link here. This was done by a researcher at in Tokyo. So she worked on this. And as for how this works, so this approaches the problem of OCR as essentially an image segmentation problem. So in image segmentation, you have something like, you maybe have a picture of a dog in a park, and you want to be able to say for each pixel in your image, well, this pixel belongs to the dog, this pixel belongs to a tree, this pixel belongs to the grass, this pixel belongs to the sky, whatever. So yeah, it's basically characterize each pixel, sort of what part of the image that belongs to. And so they've taken this approach to OCR to basically say, well, for each pixel in your image, is it part of a character or not? And if so, which one? So this uses a deep learning type of architecture called a UNet. So for image segmentation, UNet is kind of quite a common, it's probably like the standards approach now for image segmentation. The idea being that you start off with some image going in here, and you'll gradually, through some sort of like either straight convolutions or pooling or something, you'll sort of downscale it, building up more channels as you go. So you can kind of, pick up features at different scales, and then that's the sort of one half of the U, and then the other half of the U is kind of going up. So you take this sort of downscaled image, and then you gradually upscale it, so that you get to a point where you're back at the original input size with however many channels. The point being now that for each pixel in your input, you can kind of look at the corresponding pixel in your output, and however many channels you have, like each of these channels, you can take as being like the probability that this belongs to a dog, the probability this belongs to a tree, or whatever. And you also, you do this sort of like down sampling and up sampling, and you also have these sort of skip, these connections here where your information can take a more immediate path through your network. So you can kind of take advantage of information at various scales kind of passing through your network. So as I said, this is basically the most common approach to image segmentation. There are very many like tweaks you can do to exactly what kind of convolution layers or whatever you put in here, how many channels, all these sort of things. But the basic pattern of you downsample and then upsample back to your original resolution, this is kind of what characterizes a UNet. But this kind of requires you, when you're training this thing, you then need to be able to know for every single pixel in your image what character it's meant to belong to. And this is actually quite, that's quite a lot to do. So, okay. Imagine if you had to kind of go and label every single pixel here. Imagine if you had to put a box on every single character here. It's quite a time-consuming thing. So it's quite effective, but it's also relies on quite time-consuming labeling. But this is nonetheless one kind of very effective way that you can do kind of OCR. And I think this is quite a cool application of these kind of approaches. So if you don't have kind of boxes for every single character, which is probably a more common scenario. So say you're just given an image and I tell you that this image contains the word cat, but I don't tell you exactly where the C is, exactly where the A is, and exactly where the T is, then that's maybe a bit more challenging. And here, one common approach is to use something called CTC, or Connectionist Temporal Classification. And the idea being, so this is kind of I have some pictures in the next slide that'll hopefully make this clearer, but the idea being that you want to kind of find a way to, for your model to learn what to read without being given this kind of alignment information, without being told where the characters are. So what you do is you nonetheless predict characters at regular intervals in your image, but you allow for the possibility that your prediction there could be, well, there's nothing here. So this kind of blank character you introduce. And you introduce some rule, because you might have, like, if you don't know in advance how often the characters happen, so it might be that, you have a big character that's then straddles two of these prediction points. So you introduce some rules that say, well, if I'm kind of predicting A here and then A next time, we'll just collapse this. So this is kind of a little complicated. I have a bit more of a nice image. So we have an image that says cat. We have these sort of 6 slices over the image. And so for each one of these, so like take this slice in particular, we're going to predict an entire distribution across all the characters that we know for this time slice. And we'll say, here we're pretty confident it's an A, but it might be some other things. And you get one of these distributions for every single time slice. We have now 6 lots of this, which correspond to the idea that, like, what your model thinks is the likelihood of whatever character under whichever location. And you simply use these kind of rules from before to say, well, there are lots of different things you can associate to these slices that will give you cat. So this thing here is a valid way of spelling cat according to these rules. This blank goes away. This double C gets collapsed into 1. This is another way of doing it. Hopefully, I think we can share the slides at the end, yes. This is another way of writing cat. And so you can see that even though, you're not told exactly where the C, the A, or the T are, one of these will probably be kind of particularly fitting. And so the probability that you say your model assigns to the string cat is essentially the sum over all of the valid alignments that kind of make up cat. And your C-loss basically says you want this probability to be high. You want the probability of the correct string, which is defined to be the probability of the sum over all the alignments according to this splitting up that you can do. You want that to be as high as possible. Or you want the negative log of that thing to be as low as possible. So this CTC loss. So I really do recommend this Distill. Article Distill is kind of a really nice machine learning online journal which has very it has articles with lots and lots of very good interactive visualizations. I really recommend. They have a very good article on CTC. So this is another way that now you can make do with a lot less information in your labels, right? So all you need to know here is that this says cat somewhere. You don't need to know that it says the C is exactly here, the A is exactly here, and the T is exactly here. So like that's, given that labeling data is often one of these things that is incredibly costly and difficult to do at scale, this can be very effective for you. Yes, okay, and here's just an example of this. So there's the Keras docs. Keras, the sort of deep learning framework, has quite a nice tutorial of how you can do this to basically crack captures. So again, if you're interested in this is quite a nice. It's not a huge number of lines. It's quite a nice, clean tutorial. You just sort of make some kind of basic model with a bunch of convolution layers and some bidirectional LSTMs on top, so you can kind of like read from both directions, and you can see you can kind of read some relatively kind of nasty images. So that's CTC, which is another kind of approach that's often used in this OCR world. So that is my quick recap of the theory. I guess I'll probably take questions at the end about the specifics of this. Maybe go into this quite quickly. I don't know. We'll see how it goes. I'm not quite sure how to pitch this for the right level of audience, but we can recap this in a bit. I want to talk then a bit about some of the practice, because just knowing about these techniques and kind of building some kind of model out of them, that's not necessarily the same thing as having a kind of a robust product. So how do you do this in practice? So I see that there are people from all over the world, so I'm going to give a little brief introduction to Japanese. I don't really speak Japanese very well, but I can talk to this level about it. So Japanese has 3 writing systems. There's hiragana and katakana, which are more kind of syllable based, and then there's kanji, which are these kind of more elaborate kind of symbols that originally came from China. And there are lots and lots and lots of these, and you have to learn them all. So, for example, this is a kanji, I think it means tree. This is another kanji, it means eye. And there are kanji that are kind of made up of other kind of kanjis or radicals. So like that means that obviously this is some character in Japanese, this is some other character in Japanese, so you can put them together. This is a valid Japanese string. But the problem is that this is also one character in its own right. I think this means like phase or something. So kind of this, like if you see this written out in kind of a nicer printed font, you can kind of see the spacing suggests that you know, these should be separate characters. But like when you see, imagine if this kind of been written by hand in quite a quick way, it's not necessarily the easiest thing to distinguish between these. And there are lots and lots of kanji. So at school, Japanese children learn a bunch of standard kanji, just over 2,000 of them. But even that is sort of like only in some sense a drop in the ocean. There's, in terms of various sort of like standards, there's sort of standard lists that are out there. You're talking many, many thousands of kanji. And then this is not even the end of it. Some of these are kind of quite historical, but they nonetheless, they pop up, some of them pop up in quite sort of specialized situations like medical vocabulary or something like that. But this is the sort of thing you need to be able to handle. It's quite a lot more characters than just English. And yeah, there are these sort of problems like this, but it kind of gets even worse because, let's see, right, here's 2 characters. I mean, you can probably tell the difference between them, but you can also see that they do look quite similar. I mean, they are indeed basically historical variants one of another. They both mean tall. This thing on the left is probably more common. This is like a slightly older version. And because they're the sort of historical variants, it's not enough that you can kind of distinguish between them based on context, for example. So yeah, like this is a relatively common Japanese surname. It says Takahashi, means tall bridge. But like you see both of these. So it's even, you can't use this sort of hashi thing in context to sort of distinguish. You still have to kind of entertain both possibilities. And there are quite a lot of things like this. So I mean, there are many more examples, but this I think is a particularly kind of nasty one. If you look very closely, you can tell the difference. So I have, hopefully the screen will work. Can people see this? It's quite messy. Can people see this plot? If someone could confirm.
Yes, we can.
Hey, Davide.
We can live cheering for you.
Okay, so this is a big mess, obviously. But what this is, so you can take. I mean, this is something like 6,500 characters, something like that. So you can train a model, kind of like MNIST, to distinguish between all these different kanji, and you take some kind of this convolutional model, and you'll kind of build up various representations. And if you take the kind of your final representation in the model, this sort of final embedding space, and you do a dimensional reduction of that, you'll get something that looks like this. So this is obviously a mess, but you can kind of zoom in, and the idea is that the model will have learned to put similar looking kanji together to sort of like help it distinguish things apart. So all of these, clearly they have this word or writing radical on the left. And you can see that sort of this looks quite a bit like this, looks quite a bit like this. And the things that are quite close, like this looks quite like this, I would say. You can see that all these sort of quite similar looking characters are quite close together. And this hopefully is that this is quite similar. This hopefully is a good demonstration. There are lots and lots of characters, and at least at first glance, a lot of them look very similar. So let's go in somewhere like here, maybe. Again, a lot of lots of characters that look quite similar. This is sort of reflected. A lot of these are very similar, and you can imagine that in a particularly a handwriting scenario where people do write very, very quickly, that these now that become kind of very, very difficult to distinguish. So like just the simple fact that there are so many characters in Japanese really does make this kind of very challenging problem. Again, lots of things that are quite similar, but you have to find some way to distinguish between them. Oops. Can I get my slides back? So that's one of the challenges. Yeah, no, come on. Yeah. But then, like, even beyond that, there's a sort of more kind of, there's one of these things where you hit the intersection between kind of machine learning and what you can directly optimize for there and business problems, which is basically kind of what errors are important. Because the ones that you can easily fix with machine learning are not necessarily the ones that other people care about, which is always tricky. So I'm going to just get chat back. Give me a sec. Hey. So for example, here is someone's written Tokyo. And you can imagine that like you might conceivably misread this O as a 0. That, that might happen. So there are many things you can say here, but you could say that this is 80% accurate, right? I got 4 out of 5 of the characters right. Or you could say, well, this is not right at all. Like, I mean, you're either right or you're wrong. You're sort of 0% accurate. You can go by the sort of per field or per, per word, per line. Obviously this is a slightly more harsh way to judge you, but maybe this is what people actually care about. And, as you optimize your model, you're sort of directly or mostly directly optimizing for your character accuracy, but like that may not be the thing that people care about. And so how you kind of align these is one of those sort of practical considerations when you have to apply machine learning in reality. And of course it gets even more kind of important than this, right? So like this is where it really matters. We have here 1 million yen, and let's say you've misread it as 100,000 yen. Well, that's obviously kind of very bad if, it's on your loan application or your salary or whatever. You probably want to be quite careful about that. But whereas if you just kind of like imagine some of these specks of noise, one of them was a comma. I mean, it's not great, but it doesn't matter so much, right? These are somehow, they're both mistakes, but you might argue that this one matters so much more than this one. And again, like here, imagine you've missed this full stop here. Well, that's, really quite bad. There's between $123 and $12,000. So this is one of those things you really have to care about when you do this stuff for real. And basically, you kind of, there are many, many things you can measure. So as I said, you can talk about this character accuracy or sort of this field accuracy, or maybe you don't even care about that so much at all. You have ultimately some company that has an enormous amount of data, sort of enormous amount of forms, and they ultimately care about digitizing them, putting them in some kind of database. So maybe what they really care about is how quickly they can do that, or how many people are needed to check various parts of that process. Maybe that's the thing you really need to optimize for. And then ultimately, you will find the case that different customers in reality have different tolerances for errors, and this is one of those things where you really have to know your customer and make sure that what they care about is fed back into what you are trying to optimize for. It's very easy to optimize for what is easy for you to optimize for, but that's not necessarily the thing that you actually should be optimizing for, which is unfortunate, but unavoidable. And oh yes, here we go. So data. These models are all, they're trained. We know from, this is how you do the machine learning. You take an enormous amount of data and you label it in some way, and you then train the model to kind of like, learn from these labels. This is kind of classical, supervised learning setup. And one of the, things that deep learning kind of particularly excels at is making use of kind of enormous amounts of data. Like in kind of low data regimes, it's not necessarily the case that deep learning is better than anything else. It very much depends on the situation. But in general, it's when you start getting kind of loads and loads and loads of data that deep learning really comes into its own. And this is actually, it's not just a sort of a random observation. It's kind of turns out to basically be empirically verifiable in many cases. So there's this paper here from Baidu where they look in many kind of examples of things like image classification or machine translation or something like that, across many different problems. And you say, well, basically for a fixed model, kind of so you take a really good model, but then you train it with different amounts of data. I mean, how does that impact your accuracy? And it's been verified in many contexts that you often kind of end up with something that looks basically like this. You kind of get in some sort of like, you cross some threshold where you enter this kind of power law region. And what that basically means is that it's very easy for you to get sort of 80, 90% of the way there. But then each kind of little bit more, each sort of more incremental bit of improvements, you find yourself needing kind of exponentially more data. So that's obviously a challenging thing. It's very easy to get started, but these kind of like tail cases where you have particularly nasty, kind of canned or particularly nasty kind of noise patterns. Ultimately, data is king, and if you want to do this kind of stuff really, really well, you do need a lot of it. So where on earth do you get this data? Well, I mean, there are many ways. There are many kind of possible sources. Something you can do, obviously, you can generate Sapphire fonts, but this really doesn't turn out to kind of mimic handwriting particularly well. Again, you can get sort of some of the way there, but I mean, I've looked at an awful lot of Japanese handwriting data, and there really are no limits to kind of when you think you've seen all the kind of the awkward patterns and the awkward kind of scenarios that come up, like you really haven't. It keeps coming. So yeah, so you can generate Sapphire fonts. I mean, it's quite useful, but it won't get you all the way there. There's not so much in terms of certainly open source data sets for Japanese. Japanese is it's not the most friendly language for a lot of these applications because there aren't these sort of I mean, a lot of open data sets are in English, and there aren't so many things in Japanese. You can buy it. I mean, this is there are many options, but it's one of those things you just have to kind of, I think, invest time and kind of really make sure you get this stuff right. You get your data infrastructure, your labeling, okay, all this consistency, and kind of really manage your data very well. This is something that we kind of had to put a lot of effort in to, making sure you have enough data to train these things to a very high level of accuracy. And to go back to kind of natural language processing. So obviously, I've been talking here about OCR, which is mainly a kind of a computer vision type problem, at least how you approach it initially. But I mean, that's not the end of the day, right? If you kind of just go kind of character by character, you can indeed conceivably end up with a situation where you misread this O as a 0 because it kind of looks a bit like a 0. But anything that's at all language aware will say, well, that's that's kind of obviously wrong. And so these OCR models can be kind of, they can learn some sort of, depending on what you want to do, right? They can learn some sort of associations, but it's not really what they're, they are mainly computer vision based. And so you can then maybe say, well, you want to post-process using like a language model, something that has a bit more of an awareness of the structure of language, and say, well, okay, well, this clearly it's not meant to be an O. I know that there's a lot of Latin characters together, and they generally form words of letters, not numbers. And also, maybe I even know that the word Tokyo exists, and so it's probably that's what you mean. And so if you want to do this stuff again, to kind of like really, really high level, I think you have to sort of start layering on lots of natural language processing. And this can mean just like, simply, are you aware of kind of various words and kind of, patterns that they form? But you can also be much more context aware. So, things like, valid names, dates, addresses, the way that commas appear in numbers, they're kind of grouped in threes. This is something that you can kind of make use of. There are all kinds of patterns that, if you sort of start applying them to what the outputs of these sort of more vision-based things, you can kind of like correct some of the errors that come up by kind of looking at it from a different angle. And I guess I would say here that one of the things that really matters here is that your calibration has to be good, right? If your OCR model is sort of like 90% certain that this O is a 0, your language model is say 80% sure that it should correct it. Like, you want those 90 and 80% things to mean something. They don't just want to be like high numbers. It's very easy to train deep learning models that they're kind of like overconfident. And so the kind of the probabilities they give you are not so reliable. And if you kind of want to do this sort of system where you have multiple machine learning models feeding into downstream machine learning models, so one consumes the output from the other, then you kind of very quickly discover that calibration is very important here. And there really is there's so much you can do once you start applying natural language here. I mean, as I said, the point ultimately is not just to read these documents, but to kind of interpret them. And I guess maybe I can talk a little bit more about that next time, maybe. Do more of the natural language side. But I guess that's what I wanted to talk about this evening. So I guess now we can open up for other questions, and just generally, here's my email address if people want to connect with me outside of this session. But that's kind of what I wanted to say. Thank you for listening.
Cool, thank you so much, Richard. And guys, now it's time for questions. Feel free to write down your questions to Richard in the chat. And I have one more question when people are still thinking. Do you need to know Japanese in order to do everything that you said on the Japanese handwriting?
I mean, I think it's fair to say that it helps, but it's definitely not absolutely necessary. So my Japanese is pretty poor. We do have, Japanese people on the team, but as I said, it's a very international group. The majority of the people working on Tegaki are not Japanese and have varying levels of Japanese, from kind of pretty good to really not so good. So I think it's another one of those things where it's very easy to get sort of 80 or 90% of the way there without knowing anything. Some of these kind of subtleties, I think it does start eventually to get helpful to have Japanese knowledge. I mean, it's really helpful to have someone who can just sort of look at it and say, well, that's obviously wrong, or that's obviously right, or whatever. Whereas I mean, I can't do that. I have to sort of, grind some numbers or something. So yeah, I mean, it definitely helps, but you can get an enormously long way without it.
Thank you. Okay, we have a question in the chat. The first from Mark. I will read some questions in case some people will watch this workshop afterwards. Do you publish a lot at Cogent Labs? If yes, at which conferences?
Yeah, so we have published some papers. I mean, we're not ultimately, I guess the name is Cogent Labs, but I wouldn't say we're completely a research lab at the moment. We are kind of trying to be quite business focused. But nonetheless, we do have a number of publications. If you go on our website, we have a list of them. I think we presented 2 papers at NeurIPS last year. Yeah, so you can see these things on our website.
Do you personally publish something?
I haven't, no. I joined Cogent as a machine learning engineer, and so I was working a lot on the engineering side, and I've gradually moved a bit more towards the models. But I'm personally, I'm not actually that interested in research. I mean, there are people who it's much more their preference to kind of do more original things. I mean, I quite like building stuff. So I quite like taking these research ideas and then put them into practice. But we do have some people who are on the other side of that. I think it's quite a nice mix.
Cool, thank you. Next question from you. How long did it take to put your initial idea into practice, and how long did it take to introduce it as a proper product?
I don't actually know the answer to this one. So as I said, I have been at Cogent for 2.5 years. And I think Tegaki as a product has been around for maybe a year more than that. I'm not actually quite sure. Yeah, I don't quite know. I think it went. Yeah, I wouldn't want to say. I'm not sure of the answer, but I wouldn't want to say to. I think one of the things that it's once you put it out there, that's obviously not the end of the story. I think it's one of the things about machine learning models is that, well, firstly, they always benefit from more and more data, so you can continually improve them over time. But yeah, they just often can take a certain amount of maintenance. So like, people are still improving Tegaki as we go, even it's been a product of ours for a few years. So it's still kind of under some kind of active development. But yeah, I think it's been about 3 years it's been going strong.
Okay, thank you. Next question from Gao. Hello, do you recognize kanji and katakana and hiragana at the same time, or do you separate them?
So yeah, we can handle images that contain a mix of everything. So it contain like kanji and katakana and hiragana and Latin characters and numbers all in a big mix. So we can handle that all at the same time. Yes.
Okay, thank you. Next question from Spencer. Whoa, that's a bit difficult for me to read. Do you guys use CI/CD processes for your machine learning processes, or how do you effectively implement MLOps, and what tools do you guys use in this space? What cloud platforms do you use?
So Tegaki itself runs on GCP. In terms of how everything is developed internally, yes, we use kind of various sort of CI frameworks. In terms of the MLOps side of things, I think that's a little bit more homegrown, to be honest. Yeah, so yeah, I'm not sure I can say too much about that, but I think that's a little more homegrown. What we're doing on the kind of the machine learning infrastructure side. I mean, it's one of the things that, as we said, we are hiring for a machine learning engineer, and that's one of the areas that they would focus on, is sort of making it so that basically experiments can happen efficiently and that can all be put together in some sort of coherent way. But yeah, I think we're sort of a little more kind of homegrown on that side of things at the moment.
Thank you. Before we move to the next question, you mentioned about the hiring machine learning engineers. Could you just maybe describe very briefly what kind of requirements, if someone is interested, so they can proceed then with the link that you sent and look more details?
Yeah, I'll get that question. Yeah, so if people want to screenshot it or something. So there's the link. Yeah, so the more or less the team structures, we have a kind of a sort of a software and platform engineering team that kind of do a lot of the I guess the sort of the cloud infrastructure stuff, that sort of thing like Docker and Kubernetes and those sort of various of cloud infra. So they would have a team that kind of mainly focuses on that area, and then we have my team that is focused mainly on kind of building the models and kind of like analyzing the results from this. We have a couple of like researchers who are looking a bit more kind of further into the head, and then kind of so machine learning engineering is a little bit more in the middle. So we want our machine learning engineers to be kind of strong software engineers in their own right, and the sort of things that they have responsibility for are like I said, I think that data is a really key thing. So basically managing various data processes and data pipelines is a really important aspect of the role. Managing, I guess, experiment frameworks that you're going to run lots of experiments efficiently is another thing that matters. Making sure that the deployment side of things, these machine learning models, so that they can run safely and efficiently in the in the product is another kind of responsibility of the machine learning engineering team. Like it would be very easy for me to build an absolute enormous model that was completely undeployable. But even like the models that we build, they have to kind of be, you have to kind of keep track of things like your memory consumption, your speed, whether or not it can be deployed here versus there versus wherever. So deployment aspects is another responsibility for the machine learning engineering team. And we try to work quite closely. I mean, because I was on the machine learning engineering team, so I kind of, I understand that kind of side of things quite well, and I think we work quite effectively together. There's a relatively soft boundary at the moment. So it's sort of like these data processes, training, pipelines, and deployment aspects, I guess, are the main areas that the machine learning engineers focus on.
Thank you so much for your explanation. For those of you who got interested, curious, please go to the website and check the carry options that right now are published there. We move on to the next question from Savannah. Similar to Thai language, Japanese language also doesn't have a space between characters, words within the sentence. Which process do you use to help split them into individual meaningful words for natural language processing and verified context?
Yes. So this is indeed one of those challenges, that happens in Japanese. That you tend not to write it with space, but there's a sort of a continuous string where what I would think of as kind of words running one into another. So particularly for Japanese NLP, there are a number of tokenizers out there. The most common one is probably something called MeCab. So MeCab is it's a tokenizer that's sort of adapted to. It's a tokenizer that's adapted to Japanese language, and that's quite effective. There are a few other things there, but I think something called MeCab is the standard one.
Good. We got more questions coming to you. Question from Paul: Can this product be used for other languages such as simplified traditional Chinese? Because both languages obviously have similar characters, kanji.
Yes. So, one of the things we have tried to do here is to basically build as generic a solution as you can possibly get away with. There's actually not an enormous amount of sort of Japanese specific logic there, or at least not that can be switched out by other kind of, say English specific logic or whatever. I don't know if that makes sense. But we try to make the system basically as generic as possible, not have too many kind of rules, because rules can kind of certainly help you out in the short term, but they become very tricky to deal with, and you always have these sort of like kind of harsh boundaries and kind of thresholds that are a bit of a nightmare to tune. So I think you try and be as principled as you can, just to sort of ultimately, one of the promises of deep learning, which sort of is true, is you kind of put all your data in a big pot and sort of stir it, and out comes a nice model. And that, it's not exactly like that, but sort of, that, to some extent, that is kind of what happens. So we have a model that's, we have successfully trained it for other languages. At the moment, it's primarily used for Japanese, but it is a pretty generic system that we can, roll out elsewhere.
Cool, thank you. Next question. For CTC to work correctly, do you have to have a really big data set, or do you have to encode the text for the distribution to work?
I'm not sure about the last part. Sorry, I think if you can maybe comment in the chat. So to encode the text for the distribution to work, I'm not sure what that means. So I mean, I guess, you know, on the question for CTC to work, like, so, I mean, no, you can build some kind of, I mean, yeah, CTC is not anything particularly special. You can build a model that kind of has some kind of accuracy without an enormous data set. The problem is that you'll just, you know, you'll find that it doesn't kind of perform so well in these sort of like edge cases where there's kind of particularly a lot of noise or something, or where someone's written, you know, maybe, you know, if you, the problem is always, say, if you kind of get really kind of nice, clean data and train on it, you're unlikely to have a model that can deal with things outside of that distribution. So you really want, you know, basically everything you can kind of get your hands on, sort of really kind of clean data, really noisy data, really kind of carefully written data, really kind of hastily written data. You really want to kind of like get as many of these sort of patterns you can and expose the model to them so it can kind of you learn all this stuff. But I mean, certainly you can get some, you know, you can get kind of a okay-ish model from a relatively small amount of data.
Cool question from Sylvain. Do you forecast any significant leap in accuracy? Do you think it would have to do more with the models or with the data?
So I mean, yeah. So I'll go back to the. I mean, the data here clearly matters, but I mean, this is one of those things where it's not. This kind of relationship has been sort of like empirically observed in many different cases now. It's sort of like you can guess basically, if I double the size of my data set, what is that going to do to accuracy? And we've done things like, you know, you can train an absolutely enormous model, and, you know, that, again, that will increase your accuracy. Maybe sort of, they get to a point where it's impossible to deploy these things, but, you know, these are two levers, certainly, right? You can make the model huge, you can make you know, increase the data, and they're sort of, it's relatively predictable. I mean, obviously at some point these things start to flatten off, and, you know, I think we have quite an accurate system. So
maybe the question is more like at which point do you think we are on that chart?
Oh, right.
I mean, guesstimate, right?
We're probably not in the reducible error region, yeah, I would say. Yeah.
Already.
I hope not. It's going to, because that means it's kind of the end. No, I think we still have maybe a bit of a room for improvement.
Cool. Sylvain, are you happy with the answer? Then we proceed to the next question. I assume the NLP model uses transformers. Have you guys tried, or do you know if other people have tried using transformers instead of CNNs for OCR?
Yeah, I haven't seen any papers about this. I mean, so there was something recently about using transformers to get sort of, I think, sort of state-of-the-art results on ImageNet. So it is now the case that, I mean, so transformers have been used very heavily in NLP, but they're clearly coming for everything else as well. They've now been shown to be very effective on computer vision tasks. I mean, you know, I imagine it's only a matter of time.
Okay, we have two questions from Mark. The first, did any of the large GPT model results have any impact on your work? And second question is, do you ever use or find useful the open source NLP tools from Hugging Face? I think they have recently a workshop with Machine Learning Tokyo.
Yeah, so I think GPT is just English only, I think. I mean, GPT is obviously, it's a very impressive thing. And I guess it's another one of those good examples of why data is kind of king. Well, and also an absolutely massive model. Like, they're not doing anything necessarily super smart. It's just they have an enormous model, an enormous amount of data, and they get like these very, very impressive results out. But no, I think so GPT is, I mean, beyond the kind of being some sort of inspiration in kind of proving that this sort of is effective, GPT is sort of, I think it's English only, and I'm not sure that we can directly apply something like that to what we do. I mean, it's absolutely massive for starters. And for Hugging Face, yeah. So I mean, certainly, a lot of the NLP work we do is, yeah, I mean, we kind of have some stuff we've written in-house, but yeah, we also kind of make use of Hugging Face where appropriate. I mean, for people who don't know Hugging Face, it really is quite a good resource for all these, new transformer-based language models have kind of like quite nice implementations, quite nice library. It's all there, sort of easy to use. All the data sets are there. It's actually quite a nice thing they built there. And certainly, if you want to try out a new idea, then they're probably a good first place to go to. And yeah, it's certainly something that we have made use of to sort of try a lot of ideas out.
Cool, thank you. I see a couple of jokes about transformers here. Great. And we are almost on time. Guys, feel free to shoot your last questions into the chat. Like a question from Sylvain, maybe sensitive question, but do you think Google has an insurmountable head start just from the amount of data they have access to?
Well, so this is one of those things, right? So you have to assume that Google could squash most people if they decided to go into direct competition with them, right? But it's not obviously Google's interest to go into every single area. I think one of the things that we can do that Google can't, though, for example, so everything you do via Google, and so Google do have their own kind of range of like OCR and kind of related projects. They obviously, you use Google Translate, it can kind of like clearly read what's going on there. But sorry for the noise. But I mean, so all these things, they kind of run on the cloud. There are plenty of cases where businesses, for whatever reason, they don't really want to put all their data in the cloud. And so having a system like ours that kind of, can potentially run sort of on premises in sort of someone's own kind of custom internal private cloud or internal data center. I mean, this is one of the things that we offer, and this is one of the ways that you can compete with the big boys, as it were, by kind of it's not necessarily all about the accuracy or the models. It's about kind of the whole product you put it together with, right? So we can go on premises. We can, like, if we can train a custom model on your data, if that's really, really what is the most appropriate thing to do, whereas Google aren't going to do that kind of thing. So, I mean, yeah, Google obviously have way more data than we could ever hope to have. And, if they wanted to do various things with that, I'm sure they could do such things. But in practice, I think there's still a place for people like us.
Cool, thank you so much, Richard. And guys, if you have your last questions, you can shoot them very quickly into the chat, because the time is almost running over. As expected and as promised, we're having 1 hour workshop. No more sensitive questions.
Yeah. Good one to finish on.
Actually, I'm really interested in what kind of people are joining tonight, because some of them are asking very, very specific questions. So probably from the companies working on very similar products or working in the same industry. Some of the people probably are just curious, and it would be really interesting to know what you guys are, what is the goal, and what was the reason you guys joined today's event. Good. Richard, you have supporters.
Thank you.
Is that your team member?
Yeah.
Cool. If we have no more questions, and we will wrap up today's event. Okay, we have a last question from Savannah. I think UFJ Bank started to digitize their documents. Those are very sensitive data. Do you know which model they're using?
No, I'm not sure I can say anything kind of totally sensible there. Yeah, I mean, this is just generally like, you know, banks are one case of this, governments are another thing where like they really kind of care about the sensitivity of their data for obvious reasons. And so, you know, these are cases where people maybe don't like putting everything in giving it all to Google. I'm not sure I have anything to say about this specific case.
Oh, we have people sharing their background and why they decided to join the talk. It's really interesting. We have someone from university in UK teaching Japanese translation. And we also have a research PhD student interested in the Kuzushiji. That's a manuscript that you shared.
Yeah, I think that's a really cool application of this stuff. I think that's quite nice.
Yeah, when you first shared this Kuzushiji, I was like, dude, Japanese people can read it. Machine learning.
Yeah. Well, so this is the thing, right? So it's an old kind of writing system. So most people in Japan actually can't these days, which is why it's useful to kind of basically build a model that can do it for people.
A question from Daniel. Do you guys find your NLP model translatable to different customer use cases, or do you retrain it for different customers?
Yeah, again, this is one of those kind of, I guess it's kind of overlaps with a kind of a business question, right? So as I said before, we try to do things sort of as generically as possible. I mean, part of this is simply because, again, you know, it's data that really matters. It's not just about like, if you take this person's data and build a model with it and this person's data and build a model with it and you keep everything separate, then you'll end up with a whole bunch of relatively specialized, but maybe not so great models. And if you kind of put everything in a big pot together, you can build a really good one. So that's at least part of it. And part of it is also there's an overhead maintenance when it comes to trying to maintain different models for everyone that you interact with. But again, like there are always going to be some cases where it kind of makes sense from a business perspective. Like the problem is sufficiently hard, the reward is sufficiently big, it's worth the efforts to kind of for a particular customer to kind of really kind of specialize on their stuff. And this is, you know, this is one of those things where you have to kind of basically judge, is it worth it? And that's so it's certainly the thing that you can do. Yeah, it's more of one of those. There are other factors involved in this. We try to be as dynamic as possible. We can specialize if we need to.
Cool. And with this question, we are going to wrap up tonight's event. Thank you everyone for coming, participating, asking sensitive, difficult questions. Thank you, Richard, for delivering an amazing talk tonight and sharing your valuable knowledge with us. Thank you so much. And you mentioned that there is probably going to be topic for NLP topic for another workshop and talk, and I memorized this phrase of yours, and maybe we'll reach out to you for another workshop or talk we're going to have in the near future.
Yes, why not? Let's do that.
Thank you so much. We will let you go enjoy your board game with your team members.
Thank you.
Okay, let's wrap up this event. Everyone have a good evening. For those who are in Japan, good evening. For those who are in Europe, have a good day, afternoon, and see you next time at one of our workshops. Bye. Yay.